We've learned about how to quantify heat and we worked on that. So in this video, we are going to learn how to quantify and calculate the work. Okay, so as we said in the previous videos that work, you've probably heard about work in physics courses, and that force times the distance. So that's one type of work. But when we're dealing with gases, the work is defined by this equation. So it's negative external pressure times the change in the volume. Okay, so this is called pressure volume work or PV work, and the work is involved when the gas is expanded or compressed. So when the gas expands, it's pushing against an external pressure, and that's doing work. Or when the external pressure is pushing on the system, on the gas, it's going to be compressed, and again some kind of work is done. Okay, so you have a change in the volume. So you have expansion, you have an increase in volume against the external pressure, and you're doing work. Or if it's a compression, so you have decrease in volume and there is external pressure on the gas, and again there is work done. So when you're working with this equation, what are the units for work? Well, it's pressure, and that's external pressure. You have to think about that. It's the gas expands and pushing something out against some external pressure. Okay, so we have pressure and we have delta V. So what's the unit for pressure? It's atmosphere. The unit for volume is liter. So the unit for the work is, well, it's more famous to be liter atmosphere. I don't know why, where we have pressure first, so it should be atmosphere liter, but it's more common as liter atmosphere. It's a weird type of unit for work. We are familiar with Joule. We talked about the first law of thermodynamics, when we were talking about heat and work, and we were talking about energy, so that was Joule. But liter atmosphere is also a unit for work. So we have to know the bridge, the conversion between liter atmosphere to Joule. Okay, so we know that 1 liter atmosphere is 101.3 joule. So we have to know this conversion. So if in a question either of these two, sometimes you might be given volumes in liter and pressure in atmosphere, and they want work in joule. So you know that when you put these numbers in this equation, the unit for the work that you get is liter atmosphere. So you have to convert that to joule. So you know that with this equality you have in the bottom, you know that 1 liter atmosphere is 101.3 joules, so you can get your answer in joule. So this is a visual of what we were talking about. So if you have gas in the cylinder and you have the piston that can move up and down, if the gas expands, and that's basically what happens in your car. Well, there's something that ignites the gas inside a cylinder, and you have ignition and the gas expands. So when it expands, it's pushing this piston up, and you have this condition now that the piston is up, and that's a change in the volume, and you have a work is done. Okay, and that work is actually transferred into your wheels, and the car starts running. Okay, so yeah, we have the expansion, so we have increase in volume, and we are moving this piston up. Okay, so we are doing some work. So we had our equation, W is negative P delta V. So here we have expansion, right? So we have increase in volume. When we have increase in volume, what is the sign of delta V? So is it negative or positive? it's a positive delta V, right? So delta means V final minus V initial, or V2 minus V1. If we have something larger, higher value, like this one as our V final, we have higher volume here subtracted from smaller volume, so we get a positive value, right? And pressure is always a positive value. You cannot have a negative pressure. There is no such a thing. Okay, it's a something. There you have either zero or positive value. Okay, so if this is always positive, and if your delta V in expansion is positive, then what is the sign of the work? Can we find the sign of the work? Well, if you have two positive things, it doesn't matter how much it is, even if it's a very small positive number or very large positive number. But if you have two positive things and then you have this negative in the formula, then you definitely have a work as a negative number, less than zero. Okay, and that's, if we, let's have a flashback to our discussion when we were talking about work and Q signs. So we said when the system is doing the work on the surrounding, the work is negative, right? So in this system, the gas is expanding, and the gas is the system. So when the gas expands, it is pushing the piston up. Okay, so it's doing the work. So the system is doing the work. So from our previous definition, we have to say the work is negative. So the formula also matches what we've learned before. So the delta V is positive because it's an expansion. So when the delta V is positive, the pressure is positive, so the work is negative. Okay, so whenever you have expansion in gas, you will have a negative work. Whenever you have compression, you will have a positive work, because for compression, the surrounding is doing the work on the system, so the work is positive. Okay. Okay, so let's have some example. A certain gas expands from 0.5 liter to 2.5 liter, so we have expansion, right? Against an external pressure of 0 atmosphere. How much work is done? So if you think about it, work is negative P external pressure. Sometimes we do write EX as external pressure, sometimes we don't, but you have to know it's external pressure times delta V, right? So our delta V, let's write this again. So minus the external pressure. What is the external pressure? It's 0 atmosphere times, it doesn't matter what delta V is. If you have 0 times something, the answer is 0, right? But anyway, it's V final 2.5 minus 0.5 liter. So this is 2.0 liter, but this is 0, so the work is 0. So when there is no pressure, when there is no external pressure, it doesn't matter if you expand, there is nothing that pushes this back, so there's no work done. Okay, there should be a pressure, external pressure, that you're pushing against that pressure, then you're doing work. If there's no pressure, there's no work. Okay, so since there is no pressure, it's 0 atmosphere, there's no work. So let's see the other example. So if the same gas expands from 0.5 to 2.5 liter against an external pressure of 1 atmosphere, what is the work? So the formula says negative P delta V, right? So the work is negative, the external pressure is 1 atmosphere, and delta V final is 2.5 liter minus V initial is 0.5 liter. So that is 2.0 liter. And what is the work? It's negative 2.0. What's the unit? Liter atmosphere. right? So we get 2.0 liter atmosphere, but we want it in joule. So what's the conversion factor? So negative 2.0 liter atmosphere times, I know 1 liter atmosphere, I want joule. So I know 1 liter atmosphere is 101.3 joules. So therefore, this is 202.6 joule. And if you round it with 3 sig figs, that would be I missed the negative here, right? It's a -2, so negative 200 and negative 203 joules. So therefore the answer is D. So let's tie it together. If we go back and review the first law of thermodynamics. So we were talking about the signs of work and Q, right? So let's match these two things together. We talked about it a little bit, so let's see the example. So a reaction gives off heat and produces a net increase of gas when reacting. What is the sign of Q and W? So one thing you need to know that you have to see the phases. So we were talking about expansion and compression, right? So when you have more gas, it means more expansion. If you have less gas, you have less, well, you can have less expansion. It's actually compression. Okay, if you have less gas, you have compression. So looking at the phases of these reactants and products, if you're going from reactant to the product, think about the expansion and compression, and think about its giving off heat. Which one of these four is the answer? So the reaction gives off heat, so it's losing heat. So when it's losing heat, it has a decrease in temperature, or it's losing the energy. So the Q should be negative Q, right? And if you see that reaction gives more gas, well, we don't have gas in the reactants, but we are making gas, so we are going to have an expansion because of the gas. So when we have expansion, it means the system, which is the reaction and the gas, is doing work on the surrounding. We have expansion, so we are doing the work. So the work is also negative because of this equation. When we have expansion, we have positive delta V, and pressure is always positive. So because of this negative here, the W is negative. So the Q and W are both negative. So 2 is the answer. So we figured out the sign for Q and W. Can we determine the sign of delta E? Well, the Q was negative. Isn't it the Q? So the Q was negative Q, and the W was negative Q, negative W. And we know delta E is Q plus W. If Q is less than 0, it's negative, and W is negative. If you have two negative numbers and you add them, what would be the delta E? It would be a negative number, right? So we don't need to know how much work or how much heat was transferred. As long as we know they're both negative and delta E is the sum of heat and work. So the sign for the delta E is definitely negative. So in this video, we learned how to calculate the work. The work is negative pressure times delta V. And we've learned how to calculate heat in the previous videos, and we know internal energy is the sum of heat and work. So now we can find out the sign of heat and work, we can find the sign of delta E, we can calculate work, we can calculate heat, and we can calculate the change in internal energy, which is delta E.